So we now want to look at Chapter 20, Section 6. And the main thing that we're going to be using here in this section is the Nernst equation. And what the Nernst equation does is it allows us to calculate the E cell at concentrations other than standard conditions. And that is an incredibly useful thing to be able to do. So you'll remember from chapter 19 that we had this equation that delta G is equal to delta G standard plus RT natural log of Q, where Q is the reaction quotient, R is the gas constant, T is the temperature, and then delta G is not necessarily at standard conditions, and delta G standard is at standard conditions. Well, we can replace for delta G and delta G standard our formulas that are related to E cell. And so we'll replace each of those so that we get negative NF E cell is equal to negative NF E cell standard plus RT natural log of Q. Well, we're going to take both sides of this equation and divide by negative NF. And so when we do that, we will solve for E cell at not necessarily standard conditions. So E cell standard minus RT over NF natural log of Q. All right, we call this the Nernst equation, and it is an incredibly useful tool for determining how E cell changes when we change concentrations. So that is exactly what we're going to do. So let's look at a Nernst equation example. And for this one, I've chosen one. This one actually shows up in one of the labs. We don't use these numbers, but it does use the equation, so I find it useful to do this. Calculate E cell for the Voltaic cell, for the following Voltaic cell, and then calculate E when the silver concentration is 2 molar and the lead concentration is 0.2 molar. So here is our cell. So lead solid plus 2 moles of silver ion gives us lead 2 ion plus 2 moles of silver. Okay, well, first thing, we want to write the half reactions with their reduction potentials. So we'll do lead, or I guess we'll do the silver first. Silver plus an electron, silver ion plus an electron gives us silver. That has this is a value from Appendix E. It has a reduction potential of 0.799. And then we'll get lead gets converted into lead 2 plus 2 electrons, and that has a reduction potential of negative 0.126 volts. And so the cathode here is the one that we have an electron on the left side. So this is the reduction. That's the cathode. So our E cell standard is going to be 0.799 minus negative 0.126. And that's going to give us 0.925 as E cell standard. All right, so we've got E cell standard, and now we need to determine what the E cell is going to be when we change it to these concentrations. Okay, so there is our E cell standard that we just calculated on the previous page. We're going to use our Nernst equation. Remember, Q has the same expression as K, but not necessarily at equilibrium. Our product is lead 2. Our reactant is silver ion. And so we'll have concentration of lead 2 over concentration of silver ion squared. And then we'll put in the E cell standard that we just calculated. R is 8.314. Our temperature is 298. It wasn't explicitly stated there, but it was 298. Our number of moles of electrons is 2, and then 9645 for our Faraday constant. And then we'll put in these concentrations that are indicated here. So we have 0.2 divided by 2.0 squared. We'll take the natural log of that and multiply all of that out. Usually what we find is that quantity, that is the RT over NF natural log of Q, is not usually very big, but it can change the cell potential enough that it is important. So so you see here it is a relatively small number. So what we want to do is we want to look at numbers 58 and 68. So we'll start here with number 58. So number 58 on our in-class assignment. So we have a Voltaic cell utilizes the following reaction. So aluminum plus 3 moles of silver ion gives us aluminum ion plus 3 moles of silver metal. Well, I'm going to write out the Nernst equation specifically for this. So E is equal to E cell standard minus RT over NF natural log of Q. And Q, in this case, is equal to the concentration of aluminum ion divided by the concentration of silver ion cubed. Okay. So we want to think about what happens. Under standard conditions, these two concentrations are equal to 1. So it'd be 1 over 1 cubed. So Q would be equal to 1. Natural log of 1, of course, is 0. So under standard conditions, E cell would equal E cell standard. Not surprising. Okay. So now what we want to do is we want to determine what happens when we do each of these following things. We want to see how that will affect the quantity of E cell. And we may have to step through several different logical steps to get there. So we'll say water is added to the anode compartment, diluting the solution. Well, the first thing we need to figure out is which one is the anode compartment. As you recall, the anode is where the oxidation occurs. And if we look, aluminum is getting oxidized. So if we dilute the anode compartment, we're diluting the concentration of aluminum ion. So if the concentration of aluminum ion goes down, that means that Q is going to decrease. And if Q goes below 1, that means natural log of Q is going to be a negative number. So that means that if Q goes down, then we'll have negative of a negative, and that means our value for E cell is going to increase. So I will put this in the series of logical steps. So aluminum ion concentration decreases, all right, which causes Q to decrease, which in turn E increases. So whenever Q goes down, E cell is going to go up, and whenever Q goes up, E cell is going to go down. Next, the size of the aluminum electrode is increased. Here, we're just increasing the physical size of the solid. And since the solid is not in the expression, it is not going to affect Q, and therefore it will not affect E cell. So E is unchanged. So E is unchanged. Next, we've got a solution of silver nitrate is added to the cathode compartment, increasing the quantity of silver ion, but not changing its concentration. So if our silver ion concentration is unchanged, all right, that means that Q is also unchanged, which means that E is unchanged. Next, hydrogen chloride, so HCl, is added to the silver nitrate solution, precipitating some of the silver ion as silver chloride. So that means our concentration of silver ion is going to decrease. So concentration of silver ion decreases. Q will increase. And if Q increases, that means E will decrease. All right. So we want now to look at number 59, and I like number 59 because it does something that's kind of cool here. So consider the voltaic cell based on this, and we've got this. So 2Fe3 plus H2 gives us 2Fe2 plus 2H plus. So we've got iron that is being reduced. So I'll go ahead and put Fe3 plus AQ is getting converted into 2 plus. So I'll put the electron there. It's getting converted into Fe2 plus AQ. All right, and we'll look up the reduction potential for that here in just a second. And then we've got hydrogen is getting converted into 2H plus AQ plus 2 electrons. And I don't need to look that one up. I know that the reduction potential for it is 0 volts. And that's because that is our definition. But let's go ahead and we'll switch over. All right, we're going to switch over to Appendix D, and we're going to look up the iron. And it's iron 3 getting reduced into iron 2, and that one's positive 0.771. So 0.771 volts. So now we will go back. So we've got that quantity. So that means our EMF in standard conditions is going to be cathode minus the anode. And there's our cathode, there's our anode. So this one's not very hard. So E cell standard is going to be equal to 0.771 volts minus 0, which I don't need a calculator for that. 0.771 volts. And I put V twice. Let me fix that. All right. All right, so 771 volts. Okay, so that is E cell standard. Go ahead and highlight that. So 771 volts. So now it says, what is the EMF of this cell when the concentration of iron 3 is equal to 3.50, iron 2 is 0.0010 molar, partial pressure of hydrogen is 0.95 atm, and the pH of both half cells is buffered at 4.00. So I really like this problem because first of all, it's got a mixture of gases and aqueous solutions. When you've got a mixture, I'm going to go ahead and write what this equilibrium constant looks like. Our equilibrium constant is going to be products over reactants. So we've got concentration of Fe2 plus squared times the concentration of H plus squared divided by the concentration of iron 2, or iron 3 rather, Fe3 plus squared, and the partial pressure of hydrogen. And that one's to the first power because that's what the hydrogen is. So that's kind of interesting because we've got a mixture of concentrations and partial pressures. And you know, whether we're working with delta G or with these E cell kinds of problems, it is possible to have a mixture. If you've got things in the gas phase and things in solution, that is how you treat it. So I specifically actually wrote this problem just for this. So now we want to write out our Nernst equation here. So we'll have E is equal to E standard minus RT over NF natural log concentration of Fe2 plus squared times concentration of H plus squared divided by concentration of Fe3 plus squared times the partial pressure of hydrogen. All right. And since the pH is buffered at 4.0, that means that our concentration of hydrogen ion is equal to 10 to the negative 4.00. So we can put that 10 to the negative 4 in as our concentration of hydrogen. So our E cell standard is 0.771 volts minus 8.314, 298, 2 and 96485 natural log. Let's see, iron 2 here is 0.0010 squared. Hydrogen is 10 to the negative 4 squared. And then iron 3 is 3.50 squared. And the partial pressure of hydrogen is 0.95 atmospheres. And that's just to the first power. So now we need to evaluate that quantity. Okay, so I'm going to evaluate that quantity first. So we'll do 0.001 squared times 1 times 10 to the negative 4 squared. That gives us that quantity. And then we're going to divide by 3.5 squared. And then we'll also divide by 0.95. And that gives us that. So that's our value of Q. We'll take the natural log of that. So natural log of our answer. All right, and that's natural log of all that gives us the negative 34.69. And now we're going to multiply that by 8.314 times 298 divided by 2 and divided by 96485. And we'll see that our number is actually pretty significant there. So, so we're going to do equals 0.771 volts minus negative 0.445 volts. And that's going to give us a pretty significantly different answer than our E cell standard. So we'll do 0.771 minus that answer, and that gives us 1.216. So 1.216 volts. So 1.216. And so that's kind of unusual in how much it changes. But again, it's because we had this really small value for Q when we did our calculation. So now what we want to do is, well, let's see what happens to the EMF when we adjust the pH to 5.00. Well, at 5.00, that means our hydrogen ion concentration is going to be equal to 10 to the negative 5.00. So when we adjust our quantity here, we'll get E cell is equal to E cell standard, which is 0.771 volts minus 8.314, 298, 96485, natural log of 0.0010 squared, and then 10 to the negative 5 squared over 3.50 squared and 0.95. All right, so we'll clear all that, and we will get 0.001 squared times 1 times 10 to the negative 5 squared divided by 3.5 squared, and then we'll also divide by 0.95. And that is our value for Q. So now we'll take the natural log of that. Take our answer. We get negative 39. We're going to multiply by 8.314, also by 298, divide by 2, and then we'll also divide by 96485, and that gives us that. So here we've got 0.771 volts minus negative 0.505 volts. So 0.771 minus our answer, and that gives us 1.276. And that is our final answer there. So we can have a pretty significant impact on the PA, or we can have a pretty significant impact on the cell potential by changing the pH. Okay, well, we're now ready to move on to section 7 of chapter 20. We'll be looking here at batteries and fuel cells, some kind of interesting things to look at. For batteries, we'll first start with alkaline batteries, and these are the normal batteries that you're quite used to. I've got some alkaline batteries right here on my desk. Here, I'm going to switch over real quick. So some normal alkaline batteries. These are just Amazon alkaline batteries that I use for my calculator. Like I said, we're quite used to using alkaline batteries all the time. They're extremely useful. What makes them alkaline is that we've got powdered aluminum that is in a gel that is in contact with a solution of potassium hydroxide. And that potassium hydroxide is very basic, and that's why we call them alkaline. That's at the anode. We've got a mixture of manganese oxide, manganese 4 oxide, and graphite that is at the cathode. And the cell reaction is actually a little bit more complex than this, but this is a pretty good approximation of what is occurring. So the zinc plus the hydroxide gives us zinc oxide. So our zinc is getting oxidized there. That has a reduction potential of negative 1.28. The manganese here is getting reduced. It's going from manganese 4 to manganese 3. And that is, and so that's getting reduced. That's 0.15. When we do the difference there, we get 1.43 volts. And that gives us most of the 1.5 volts that we have for a typical battery. One of the things that's cool about this is that you'll see everything here is in the solid phase, which means that that our value for Q is 1, which means that the cell potential of our battery doesn't change a whole lot over the lifetime of the battery. Now, it does change a little bit. There's nothing we can do to avoid that. It does change a little bit because there are some irregularities that occur, but it's a very reliable way to store energy in something that is relatively safe to carry around. Now, of course, that potassium hydroxide, we want to make sure that that doesn't get out. So you never want to take these batteries and break them open or throw them in a fire or anything like that, because some nasty stuff can happen. But that is how a typical alkaline battery will work. Next battery is the lead-acid batteries. These are the batteries that are inside of your car. So lead-acid batteries use lead oxide at the cathode and lead at the anode. And since both of those are solids and both of the reactions are in acidic sulfuric acid, that means that we can put both electrodes into the same compartment. As long as the two electrodes don't come in contact with each other, it should work just fine. Now, if they come in contact with each other, the battery is shorted out and it won't work anymore. But as long as they don't come in contact, we should be okay. So that is our cathode. This one is our anode. If we do the difference and add them together, we will get this. So that's pretty much sulfuric acid Both of them, interestingly, have lead-2 sulfate as the product. So on this one, we have lead-4 going to lead-2 in the reduction at the cathode. And at the anode, we have lead-0 going to lead-2 sulfate. Since they both have lead sulfate as the product, that means that if you let the reaction go on too long, you'll find that your electrodes will get converted into lead sulfate. And if you've ever had a battery that, like, you've left the lights on in your car, if you've left the lights on or something like that, and you take it in and they say, "Hey, can I recharge it?" And they'll say, "No, it's been sulfated." Well, that's what they mean, is that we've got that lead sulfate. It's been sulfated. Once it's been sulfated, there's no recovering. You trade in your battery at that point. And by the way, because of the sulfuric acid, it is important that you, and even more important because of the lead, it's important that you always dispose of these properly. Wherever you purchase your next battery, they will take your old battery. And in the state of Texas, there's a core charge for each battery, and I believe it's about $10, and that's just an incentive to trade in your battery, and you'll get, I think, $10 you'll save the $10 core charge on your next battery. So if you don't have a battery, if you're just buying a brand new battery, you'll have to pay that core charge up front. So I just mentioned that because they definitely don't want you just taking these and throwing them into the landfill. The lead is quite toxic and not something that we want in our water stream. Okay, and in case you're wondering, a typical car battery is not 2 volts. A typical car battery is 12 volts. So the way they achieve this is they actually put 6 of these of each plate, so 6 anodes and 6 cathodes, all in series, and are able to add those, so 6 times this, and that will give you the 12 volts. So that's how you get 12-volt batteries. You can get more if you put more plates in, but the standard is for a 12-volt battery. All right, these batteries are really, really useful. They do have the downside, as I mentioned, of the lead being quite toxic, and they also have the downside of lead being very, very heavy. So lead batteries definitely have limitations. All right, so we're going to look at lithium-ion batteries, which have some really, really cool advantages and also some limitations as well. So lithium-ion batteries, they have an extremely high, what we call a high specific energy and a high specific energy density and a high volumetric energy density. And what that means is you can get a lot of energy into a very small package. And that is what makes them so useful for electronics. You'll typically get approximately 3.7 volts of cell potential per cell, and you can add those together, so you can get 3.7, or you can get twice that, which would be what 7.4, and triple that, and so on. And so you can get multiples of that 3.7, and that will work. Now, the actual chemistry behind it is a little bit complex, more complex than I'm willing to talk about in this class, because the stoichiometry gets really, really weird. If you're interested, you can just go and look up lithium-ion batteries, and the Wikipedia page actually has a pretty good explanation of it. But I'm going to warn you that the chemical equations they don't look like the normal ones that we've done, because there's some weird fractions that occur there. So very complex reactions. One of the downsides of the lithium-ion battery, the lithium is moderately expensive, but these all require cobalt to make them work. So the cobalt is an important component of this, and without that cobalt, it doesn't work. And cobalt is a relatively energy-intensive metal to mine. So since we're constantly using more of these lithium-ion batteries, there is a constant need to get more cobalt from mines, and so we just have to keep that in mind when we're using these. So we also want to look at hydrogen fuel cells, which are pretty cool. Hydrogen fuel cells, they use the reaction between hydrogen and oxygen. So hydrogen is getting is getting oxidized here, and then this oxygen is getting reduced. That gives us a difference of 1.23 volts. All right, that 1.23 volts, just like with other things, we can multiply that. If we do multiple fuel cells in series, we can get multiples of that if we need to power something. So these are about twice as efficient as using hydrogen just to burn it. So if you want to produce electricity, using a hydrogen fuel cell is a lot more efficient than burning the hydrogen and using the heat energy to produce electricity. However, in order to make this work, there's a very, very expensive platinum catalyst that is used to make the hydrogen, or to make this the chemical equation work without the hydrogen and oxygen like catching on fire. So, and you do need a pretty pure source of hydrogen and oxygen coming in, so there are some limitations there. However, for very remote uses, like perhaps on the International Space Station or some other satellite that's going to be in space for a long time, we will find that this kind of thing makes sense, because you can regenerate the hydrogen using solar cells, and so it is a little bit different. Now, technically, we don't consider a hydrogen fuel cell a battery, because we do need a constant flow of hydrogen gas as fuel to make it work. But they do work on electrochemical principles and are pretty cool. Hydrogen gas is not something that you would just get out of the earth. Hydrogen gas is something you have to produce, so it takes energy to produce that hydrogen gas. Okay, so that is the hydrogen fuel cells. And I want to talk very briefly about corrosion and the process of corrosion. So here is corrosion of a metal, and the metal here is iron. So iron can get oxidized. It'll form iron 2. Then there's a subsequent reaction that will form iron 3. And when you form the iron 3 oxide, that is rust. So we call that the process of rusting. The key components that you need to make this happen is that you need iron, oxygen, and water. And if those things are present, then the iron is probably going to rust. However, there are things that we can do to the iron to make it less likely to rust. For example, there are certain metals that we can mix in as alloys that will decrease the likelihood that the iron will rust. And that's the case in stuff like stainless steel. However, if it's just exposed, if it is just exposed to water and oxygen, it eventually will rust. So there is some electrochemistry that we can use that will protect the iron and keep it from rusting and keep from having structural failure. So we call this cathodic protection. So what happens is that you put a thin layer of zinc. And so if you have zinc on the surface, the zinc will get oxidized a little bit, and the zinc will act as the anode, and the iron will act as the cathode, and that prevents it from getting oxidized. And as long as there's some zinc on the surface, then your iron will not rust and it will maintain its integrity. Another word for iron that's been treated this way is galvanized. So if you have galvanized nails, that means they have a thin layer of zinc on the outside, and that will protect them from rust for quite a long time. So, these kinds of galvanized nails and screws and things like that are recommended for projects where you're going to have those outside and they will be exposed to the elements for years and years. Then definitely you want to get galvanized things that will protect them. Another kind of application that's similar to this is if you have iron pipes. So here is an iron pipe that you might see, an old iron pipe. Most modern new installation pipes are either going to be, if they're really big, they may be concrete or something like that. Or if they're, if they're just like in your backyard, they may actually be plastic now. There are some pretty high quality plastic pipes that they can use, like for your sewer line or something like that. But for old construction, there are iron pipes, but those iron pipes are underground with lots of water. There's oxygen available, and so those iron pipes can rust. Well, you don't even have to necessarily completely coat it or anything. Instead, you can just attach a sacrificial electrode, like this one that's made out of magnesium. It will oxidize, and the iron will act as the cathode, so that will prevent it from getting oxidized. The magnesium will end up getting oxidized, and then just whenever that magnesium gets used up, you can replace it with a new one. You solder a new one on, and you can replace it. This is how they protect things like the levees down in New Orleans. Those levees are made of iron, and they're right there on the ocean. They're holding the ocean back, and with all that salt water and oxygen and water, of course, those things would just rust right through pretty quickly if they didn't have these electrodes. So periodically they'll send swimmers down and replace them. They'll weld on some new ones, and pretty cool technology. So, all right, we're now ready to talk about our last topic, which is electrolysis. And electrolysis is the process where we purposely make a reaction go in the non-spontaneous direction. So we can force non-spontaneous reactions to occur if we have an outside source of electricity. And so here is an example. Normally, if we had sodium and chlorine, and we put those together, it would make sodium chloride. Well, we can take sodium chloride and convert that into chlorine gas and sodium metal. But to do that, we need to melt the sodium, and molten sodium chloride is a pretty good electrolyte. So it will conduct the electricity. And if you apply this potential across there, and again, you need an outside direct current source. You apply it, you will oxidize, you will reduce the sodium plus 1 to give us sodium liquid, and you can isolate that liquid molten sodium, and the chloride you can oxidize to form chlorine gas. And usually these two things work in tandem. The chlorine goes on to make stuff like bleach, and the sodium goes on to make things like caustic soda, like sodium hydroxide, those kinds of things. So this is a very huge volume operation that is done. But this process is called electrolysis. So where you use chemical energies to make reactions go in the direction that you want, that is called electrolysis. So when we're talking about electrolysis, we're going to have what we refer to as electrolytic cells, and these are different than voltaic cells. And I want to point out a few of the similarities and a few of the differences. As far as, is it spontaneous? Well, our voltaic cells are spontaneous. They will go to equilibrium on their own, whereas electrolytic cells, we force them to go in the non-spontaneous direction. So we would say no, electrolytic cells are not spontaneous. We'll find for voltaic cells, oxidation will occur at the anode and reduction at the cathode. For electrolytic cells, it's the same thing. So oxidation always occurs at the anode, reduction always occurs at the cathode. And that doesn't matter what type of cell it is, that's always true. The signs of the electrodes are opposite for electrolytic cells, and I'll explain that by going back to this picture here in a second. But in a voltaic cell, the anode is negative because that's where the electrons are coming from, and the cathode is positive because that's where the electrons are going to. In an electrolytic cell, it's the opposite way around because we're looking at it from the perspective of the outside energy source. So I'm going to go back to this picture. The reason that we would call the cathode the negative, because here is our outside energy source. So we have electrons flowing this way. Since there's a source of electrons here, we call this the negative electrode. And since the electrons are being pulled away from the anode, we call this one the positive electrode. It is just a convention, so try not to get too terribly confused about it, but you do need to know that for voltaic cells and electrolytic cells, the sign convention is opposite. So let's look at an electrolysis problem, and this will be the final topic that we'll talk about in this chapter. And so when we're doing electrolysis, we usually are trying to force a reaction to go in a non-spontaneous direction, or finding one that wouldn't happen on its own to go in a particular direction. Here is the setup if we wanted to nickel plate something, and this works for chrome plating as well. We'll talk about chrome plating here in just a moment, but when we nickel plate a particular object, so let's say we've got a steel ring here that we want to nickel plate. We want to put a thin layer of nickel on the outside as a protective layer and as perhaps a decorative layer. Well, we'll have an anode where nickel is getting oxidized, so oxidation occurs at the anode. So nickel gets oxidized to form nickel 2 plus 2 electrons, and then at the cathode we would have nickel 2 getting reduced to form nickel. So you'll notice it's the same reaction at both electrodes. So however many nickel ions you get turned into nickel atoms at the cathode, you're going to have the same number of nickel atoms getting converted into nickel ions at the anode. That's convenient because our concentration of nickel isn't going to change in that solution, and that's a convenient thing to do. So what we want to do is we want to look at this problem. So calculate the number of grams of nickel that will be plated onto a steel object if a current of 1.45 amperes is applied over a period of 2.25 hours. Well, an ampere is a unit of current, and 1 ampere is equal to 1 coulomb per second. So we are going to use a sort of a flow chart. I call them a roadmap to help us determine the answer to this. So the time, the charge, and the current are all related to each other. Current is equal to the charge divided by the time. And so if we know one of those, if we know two of those, we can get the third. So here we know the current and we know the time. And so therefore we can get the charge. From the charge, which that charge will end up being in coulombs, we can convert from coulombs to moles of electrons using our Faraday constant. So we can convert from coulombs to moles using our Faraday constant. And then we can go from moles of electrons to moles of nickel, and that's because for every mole of nickel that we plate out, we're going to use up 2 moles of electrons. So we'll have 2 moles of electrons there. Then we can convert from moles of nickel into the mass of nickel, and we just have to use the molar mass of nickel. And that's how we do this. So now I'm going to show you the process here. So 2.25 hours. We do want to convert those hours into seconds. So 60 minutes times 60 seconds is 3,600 seconds per hour. So we multiply by 3,600. So that gives us our time in seconds. We're going to multiply by the 1.45 amperes, which is 1.45 coulombs per second. So you'll see our seconds cancel out. Then that gives us the charge. We're going to divide by the Faraday constant, which is 96485 coulombs per mole of electrons. So now our coulombs will cancel out. That will give us our moles of electrons. And then from moles of electrons, we'll get to the mole of nickel. There are, for every mole of nickel, there are 2 moles of electrons that are consumed. So we'll have 1 over 2. Our moles of electrons cancels out. And then finally our molar mass, our moles of nickel will cancel out. And that will give us 3.57 grams of nickel will be plated out over that period. So we're going to do a similar problem. This time it will be with chromium, and this will be on number 85. So we'll switch over. So here we go. We've got our problem here. So we've got a chromium-3 solution is electrolyzed using a current of 7.60 amperes. What mass of chromium is plated out after 2 days? So the reaction that is happening at the cathode where it is being plated out is chromium 3 plus 3 electrons to give us chromium solid. And we're going to need that 3 moles of electrons for every 1 mole of chromium here in a little bit. So what we know is we know the time and we know the current. So we're going to write out our little, what do you call it, our little road map here. So we've got our time and our charge, and then that is related to the current. Okay. And from the charge, we're going to convert into the moles of electrons. And for that, we're going to use the Faraday constant. From the moles of electrons, we can go to the moles of chromium. And for that, we're going to use the 3 moles of electrons for every 1 mole of chromium. And then for moles of chromium, we'll go to the mass of chromium. So that gives us a plan. To solve this. So now let's do this. So we'll start with the 2.00 days. So 2.00 days, and we'll need to convert that into seconds. So we'll have 24 hours is equal to 1 day, and 1 hour is equal to 3,600 seconds. All right. Our current is 7.60 amperes, so we're going to multiply by 7.60 coulombs per second. So 7.60 coulombs per second, and that gets us to the charge. So you'll see days cancel out, hours cancel out, seconds cancel out, and that gives us the charge. Well, then from the charge, we're going to go to the moles of electrons, and we're going to use that Faraday constant, which is 96485 coulombs per mole of electrons. From moles of electrons, we'll get to the moles of chromium. There's 3 moles of electrons that are used up for every 1 mole of chromium. So we'll have 3 moles of electrons for every 1 mole of chromium. And then finally, we will convert from moles of chromium to the mass using the atomic mass of chromium, which I have right here, 51.996. We're going to call that 52.00. We'll put 52.00 grams of chromium per mole of chromium. And if you feel up for it, you can go through and do the dimensional analysis and cross out each of the units, but you'll see that it definitely works out. So easy enough. We'll do 2. All right, make sure you can see this. So 2 times 24 times 3,600 times 7.60 divided by 96485. All right. We'll also divide by 3, and then we're going to multiply by 52.00. And the number we get there, 235.92. Let's see, we've got 3 sig figs, so we're going to write that as just 236. So 236 grams of chromium. So that is the mass of the chromium. So next, here it's saying what amperage, in other words, it's saying what current is required to plate out 0.25 moles of chromium from a chromium-3 solution in a period of 8 hours. Well, to solve this, our current is equal to the charge divided by the time. And that time is in seconds, and the charge is in coulombs. So we need to take the moles of chromium. So here's moles of chromium. We need to go back 2 steps to get to the charge. And then for the time, we need to convert those hours into seconds. So for the charge, I'm just going to put 0.250. I'm going to go down 1 here. So I have plenty of room. So 0.250 moles of chromium. And let's see, so 0.25 moles of chromium, and for every 1 mole of chromium, there are 3 moles of electrons. And then for every, let's see, we have 96485 coulombs per mole of electrons. So that gets us the charge. Our time was 8 hours, so 8.00 hours. And we'll just do 1 hour is equal to 3,600 seconds. So you'll see hours cancel out, moles of electrons cancels out, and that's going to give us coulombs per second, and that is the current. So we'll clear all that, and we will put 0.250 divided by 8, and multiply by 3, multiply by 96485, and then we will divide by 3,600. And that gives us 2.51 amperes. So 2.51 amperes, and that is our current. And then, go back over here, our next page is the last page. That represents the end of chapter 20. So next chapter coming up, chapter 21, and we will be done.